right.
That always peps me up.
Yeah, me too. So for those who just joined us, I had a major Freudian slip right before the entry. So you guys can go back and watch that. We are on session 6. And yeah, so how are you two been? Having
Doing
a good week?
good.
Cool.
Yeah, I've been doing really good. Not as restless as I was, Sunday. I don't know what it was. I got a turntable for one thing. And so I had some old albums, and I don't know, I just had this really strong nostalgic feeling going on. And then just this really restless feeling. I mean, it was like I couldn't hardly sit still. It was just really strange. So that's calmed down a little bit.
Yeah, I know you mentioned
That's
Sunday
good.
at our book club that you were, feeling just off.
Yeah, it was
So,
really
okay.
strange. And so it's kind of still there, but it's not like it was. So I don't know.
Yeah.
Just
Okay.
me
Well,
being weird.
It sounds
glad
like
you're feeling back yourself.
it sounds like anxiety, Carrie.
Mm-hmm.
Maybe a little bit, but it could have been. And I don't know, I've because, we start thinking about, well, what did I eat? Did I eat something that, may have, and I can't really think of anything just off the top of my head that I would have, because I mean, my meals are very dull. I mean, it's the same old thing
Yeah.
over and over. So I don't know, but it was
Well,
really kind of an odd mood.
Sometimes you have just like a longing for, I mean, I don't even want to say the past, but like more of a longing of togetherness, with family and stuff that you may not see anymore, or friends that you may not see anymore and be with. I have that a lot, I want my family and stuff to get together, but I can't think of a solution for it because it's going to take a big place to do it. And, I used to have a cousin that would have parties all the time, and I just like miss that so much, and sometimes that music can bring about feelings of,
Yeah. And my best childhood friend, recently passed too. So, I went to her funeral was a couple months ago.
sorry.
And that really affected me a lot.
Did you used to listen to records together?
Oh yeah. I mean, I was introduced
Maybe
to
that
rock
could have
and roll.
triggered.
Yeah,
maybe
with
that
her.
just getting the turntable could have triggered something for
Yeah, I mean, we stole records from her older brother, Timmy. We stole his records, and she had what I call a little box record player in her room, and we stole his records and snuck them in there. So I learned all about Kiss and Nazareth and Bad Company and Ted Nugent. I learned about all them through, stealing his records.
Yeah.
So I talked about that at the funeral, actually.
Oh,
Yeah.
yeah.
All right. Hey, Arlene.
Hey, Arlene.
It's hard getting older because, the older you get, the more people you lose and stuff. And it's hard, I mean, I'm grateful that I'm healthy, but, it's hard.
Yeah, definitely.
Well, I'm trying to make new memories. I went and I've been doing all the stuff to get my passport. So I had already gotten my real ID, that new thing that you have to be able to fly next year. And so now I'm going through the process of getting my passport. And I went and got my passport photo taken, and they used worse lighting than the DMV. I swear.
Oh no,
I look terrible. But anyway, I'm getting it done. I may get a do-over on the pictures because I'm submitting the paperwork in a couple weeks. You have to schedule an appointment for that. So. Yeah. But I'm working on that, and I'm going to do some traveling.
Good.
Make some new memories. Yep.
Excellent. All right. So are you both ready to get going? Dive in for today?
We can dive on in.
All right.
So who started the reading last week?
I think it was me.
Okay. Well, I will start this week. I already got a comment from Arlene. I hurt the ball of my big toe on Saturday when I did both challenge workouts. I know I'm beating that ball, my viewers here. Okay, feel better. Good. Okay. Okay, good, 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 good. Oh, and Charlie's here. Hey, Charlie, we missed
Hey,
you on Sunday.
Charlie.
Charlie,
Let's see.
I'm jealous. I wish I had some
Tell us
tallow
fried
fried
chicken
chicken
skin.
skins.
Mm.
Nice. Did you
That
make?
sounds
Do you make
yummy.
them yourself? That would be good because I know that my husband loves chicken skins, but the ones that we've been ordering have like sunflower oil in them.
Oh,
That's what they're made with. I would
No.
make them myself, but
Yeah.
yeah.
I
okay.
make them myself, but I'm sure they're not quite as tasty as they would be if I fried them in tallow.
Mm.
Yeah, maybe not. Okay, and you know what? I remember too. I have slides, so let me pull up. I don't want to pull them up just yet, but let me just at least have them ready because I think that the next, yeah, I'll pull that up when we're ready for it because we've got several diagrams in the next few pages.
Mm-hmm.
Okay, so we are on section 1.2.2.1.1. It's called basal insulin release. Oh, and let me just kind of give an intro because I know that like we see people in the live chat that are regulars, but just in case someone pops in who has not joined us yet, let me just introduce what we're doing. Quickly, we are going through this textbook, and it is a textbook, Ketogenic, the Science of Therapeutic Carbohydrate Restriction in Human Health. And this is not a book club. This is a study club. We have not pre-read. We are reading to each other, and we're going to read and discuss, and we're working our way through this book. So if that sounds interesting to you, stick around. It's a very different way of going through a book. Online, that is. So,
Right.
okay. Alrighty. So basal insulin release. So insulin is typically described as being released from the pancreas in both a basal and bolus response to maintain homeostasis. Although this model is likely an oversimplification of a complex process. The mechanism by which basal or fasting insulin is secreted is not fully elucidated, but theorized to involve both serotonin and osteocalcin and or the incretins. It is estimated that the basal rate of insulin secretion is 0.25 to 1.5 units of insulin per hour, and that your basal secretion amounts for approximately 50% of total daily insulin. Basal insulin is released from the pancreas in a rhythmic and pulsatile manner with circadian and ultradian periodicities. I don't know what ultradian means. Maybe one of
Me
you can look
neither.
that up while maybe you can look that up while I'm finishing this paragraph. As depicted in figure 1.3. So do I have figure 1.3? I do.
Okay, let's see. Ultradian rhythms are biological cycles that repeat throughout the 24-hour day, but are shorter than a day and longer than an hour. They are a type of short-term rhythms with periods that typically range from 20 minutes to 6 hours.
Okay. All right. So that makes sense based on the diagram. We can see that there's these little undulations, but there's also like big waves.
I didn't
So this is
realize insulin did anything unless you actually needed it. Like,
That's news to me also.
well, I'm assuming that we always need some baseline level because of the just basic functioning of our cells in in its resting rate.
Yeah, I
So
guess
this
that would make sense just because, I mean, even sitting here breathing, I'm using some amount of,
yes. Yeah, absolutely. So
sugar.
on a cellular level, we have, we have metabolic needs. So I'm assuming that's why we need to have a constant, secretion. Well, I guess it's not constant. It kind of peaks, it has peaks and valleys, but this says a conceptual model of the oscillatory nature of insulin secretion in a fasted state. So that's the top chart there. And that's the first little dip, it goes up, and then the first little dip is at 120 minutes. So it looks like there's like 120-minute cycles.
Wow.
Okay. Yeah. So Amy says your body makes insulin even if you're not eating any carbs. So you get some insulin every single day. Couldn't tell you how much, but I know it does make its own insulin. Yeah. Yeah. So your pancreas is always doing that work. Okay. So that's what ultradian means. So okay. So I'll take that down because I think that's all we need from that one. Okay. So although the ultradian periodicity ranges from 40 to 180 minutes, this is further modulated by fast oscillations that vary between 5 and 15 minutes. And those are those little tiny undulations we saw as it was going up and down and up and down. It was giving these little tiny oscillations. These latter oscillations are believed to be influenced by the individual's personal degree of insulin resistance. Finally, insulin is secreted in pulses from the pancreas approximately every 4 minutes. Calcium and/or CAMP oscillations are hypothesized to be the direct cause of the insulin oscillations. Okay, so we've got oscillations of electrolytes and other chemicals that are basically influencing the oscillations of our insulin. So, okay, so that's any thoughts on that one?
No, I just didn't realize. I mean, and of course, I know that Ben Bickman talks about insulin is most famous for, bringing down your glucose, but it does lots of other things. And I guess I just never really considered that it was that, that there was so much going on with it. So that's pretty interesting.
Yeah. Well, and I mean, we saw last week, and I can put this table back up, but we saw last week, this was this list of all of these things that stimulate insulin release from the cells.
Mm-hmm.
Glucose is only one of them.
Yep.
So obviously there's interaction between our, beta cells and more than just the glucose. So I remember
And the CAMP stands for cyclic adenosine monophosphate, a small molecule that acts as a second messenger within cells and is important in many biological processes. It's a derivative of ATP and is involved in signaling pathways such as glycogen metabolism, gene regulation, and olfactory sensory transduction. It's also a key regulator of immune cell functions and therapeutic strategies that affect CAMP generation or effects could have immunoregulatory potential in autoimmune and inflammatory disorders. So basically, that's that in calcium. It said oscillations are hypothesized to be the direct cause of the insulin oscillations.
Oh my goodness.
Okay.
Wow.
Okay.
I mean,
so
it's complex.
Our body is, yes, everything is interacting with everything. So cool. Okay. All right. So that is that section. So Carrie, there's a small section and then
1.2.1.2 bolus insulin release. The biphasic mechanism by which bolus insulin is released following glucose stimulation is well established. Briefly, glucose enters the beta cell via glucose transporters, GLUT or GLUT, stimulating mitochondrial oxidative ATP synthesis. Although traditionally believed to be GLUT type 2, accumulating evidence suggests that GLUT1 and GLUT3 are predominant in human pancreatic beta cells. An adequate amount of ATP closes the K-ATP channel, leading to depolarization of the cell membrane, which triggers an influx of, I guess that's calcium?
Calcium, yeah.
Okay. Resulting in exocytosis of insulin stored in readily releasable vesicles. In a healthy person, this first phase insulin release should occur over approximately 15 to 30 minutes, depending on administration route. and leads to the 30-minute insulin peaks seen on oral glucose tolerance tests. Okay. The second phase of insulin secretion likely represents both readily releasable and reserve pool vesicles and is induced by fuel secretagogues. The second phase is characterized by a nadir following the first phase and has lower amplitude and longer duration and lasts as long as the stimulus on the beta cells.
I
The
don't know what a
rationale
nadir
for
is.
Hmm?
Can we look up nadir?
Yeah.
Because I have no clue what that is. Let's see.
Yeah, that's the lowest point. I was thinking that was it, but I didn't want to say it wrong. The lowest
Okay.
point.
Okay.
So I guess the lowest point the insulin's going to get.
Okay, interesting. I hadn't heard that term before, or
Wow.
didn't remember hearing it.
I hadn't
Okay.
Yeah,
either.
I've heard it a lot, like in medications. I'm thinking like vancomycin, or I don't know. I've heard it like at work.
I mean, I've always like with Vanco, I've always heard of like the peak and the trough.
Yeah, but
and
I think
hadn't heard.
I can't remember. But I was thinking it was the lowest point, and that was it.
Yeah,
So.
well, you're right. So, yeah.
Wow.
Okay. So yeah, good. The little learned a new word.
We've
So
learned a
basically,
couple of new
phase,
words.
yeah. So the second phase is characterized by basically a low point following the first phase. Okay.
And so this falls into, it talks about that, like there are people who are like carnivore or very low carb who fail that glucose tolerance test because they don't have that storage of glucose that most people do, or they don't have as much to bring it down. And so they fail that test. I've heard Ben Bickman talk about that too, and others, but he just comes to mind. So, okay, this is tying together here. So I'm glad we also have you medical folks here so to clear things up.
I don't know about that.
Well, at least we can Google it and Google terms,
We
right?
can throw a general educated guess at it, right?
Right.
Well, so far so good. The rationale for pulsatility is that it is more effective at reducing blood glucose concentration and is hypothesized to reduce the risk of downregulating the insulin receptor, INSR, through overstimulation. The ultradian periodicity is tightly coupled with ultradian rhythms of the neuroendocrine, cardiovascular, and autonomic nervous systems and contributes to sympathovagal balance. And I know I probably mispronounced that one. Is it sympathovagal or vagal? Vagal?
Vagal. Yeah, because it's talking about the vagus nerve.
Vagal. Okay. Suppression of insulin secretion is mediated via a variety of hormones, including somatostatin, corticosteroids, and catecholamines, especially. Okay, what is that symbol there?
That looks like alpha-2 adrenoreceptors.
Okay, alpha-2 adrenoreceptors, with the latter two typically during stress or exercise.
Okay, so it referenced the second chart here, which is the conceptual model of biphasic insulin secretion in response to a glucose bolus. So basically, that's what our insulin does after we eat. Is it takes us, it starts there where a basal insulin level is, which is at a fasting rate down towards the bottom, and then we get a spike after it's introduced to glucose, and then should, I guess if it's working properly, it should come down pretty quickly. I mean but there's two phases. I don't remember, and I don't know about you, Kim, but I remember, of course we administer insulin a lot as nurses in the hospital, and you talk about postprandial blood sugars, which is like 2 hours after eating. I didn't know that it had these two phases in the meantime. I mean, all of this is in like 80-minute timeline.
Yeah, I don't remember the biphasic nature of it. I just remember that, certain insulins act over a longer period, and, the short acting, the long acting, intermediate, all that. But I don't remember the biphasic nature of just our insulin.
No, I didn't either. And I don't know how this correlates to actual blood sugar readings, because this is a spike of insulin. And so, and it obviously goes down almost to the basal level, but then it kind of creeps up again in that second phase. So I don't know how this correlates to actual, like if you're to take maybe every, 5 minutes, take a blood sugar reading, how that would correlate to the actual blood sugar. But that's kind of new information for me.
I mean, I've worn a CGM and I didn't see anything that would resemble, a result of your insulin doing that. But now
you would think that if it did, it would be like the inverse, like you could flip the chart, flip it on its head, and it would be the absolute inverse relationship. As the insulin goes up, the blood sugar spikes down. But so you didn't see that at all.
I do see a result of that first phase. And mine is very responsive, which is surprising to me because I know that I'm insulin resistant, at least to some degree, right? And so it's kind of surprising to me that even if I were to eat something that was higher in sugar, let's say a fruit of some sort. I don't eat much of that these days, but like when I was wearing the glucose monitor, I did test some stuff out, or let's say a coffee drink that I didn't realize the sweetener in it had a little more sugar than I thought. And I would notice, my sugar would go up to maybe 130 and it would come down so quickly. I was surprised at that. Like I was surprised that it knocked it down so quickly, considering that I have insulin resistance,
Yeah. Well, that must have been that first phase because that big peak is within the first 10 minutes.
Yeah. And it was just that quick too. Like you would notice, and I guess that's probably the difference between like me and a full-blown diabetic, maybe, I don't know. But you would notice that it would, like within 10 minutes, it was 130 and then it was back down, to like 110. So it was kind of surprising. But I do
would it go back up again? Would your blood sugar go back up again during that second phase?
No, I didn't know.
So maybe that's the insulin needed. Maybe that second phase is just like the first peak is the insulin needed to get your blood sugar to make that first jump down. And then the second phase is the amount needed to keep it down.
Yeah, I don't know.
Just theorizing here.
So I wanted to say though,
oh, go ahead.
Can I say something real quick? I do remember now where I heard the term nadir. We use it when you're talking about the blood cell count during chemotherapy. In oncology, nadir is used to describe the lowest point of a patient's blood cell count during chemo. And I used to give chemo, so that's probably where I've heard that.
Oh, okay. Is it like the neutrophil counts?
It's the I believe so.
Yeah. Okay. All right. Okay. So it was not related to blood sugar or insulin, but it was a term that was used. Yeah.
Basically the term nadir can be used for anything, but it means lowest.
Yeah. So it was actually like in practice. Okay, cool.
It's commonly used in medicine.
Yeah.
Hmm.
Okay, cool. I never worked in oncology, so I guess that would make sense why I had never, I don't recall hearing it. All right, so Cynthia's got some feedback for us. So she says, I think the first phase is like the savior of the sudden blood sugar spike after eating. Then the pancreas is put to work and delivers more insulin to stabilize the blood glucose over time. Awesome. Awesome.
Yeah,
She
that
says,
would
I don't
make
know,
sense.
just a thought, but that makes total
It
sense.
does make
Yeah.
sense.
Yeah.
Yeah. That's kind of the way I was interpreting the graph. So, okay, cool. All righty. So, Kim, you want to take these next couple of sections because this first
Yeah.
one's really small. Yeah.
Okay, so insulin, section 1.2.2.2, insulin, mechanism of action. All of insulin's physiological effects occur following binding to the INSR, which is the plasma membrane of many different somatic cell types. It is suggested that lower insulin does invoke metabolic effects, while larger amounts invoke mitogenic effects, with the latter predominantly via the mitogen activated protein kinase pathways, or MAPK pathways. Section 1.2.2.2.1.
You want to know the meaning of mitogenic?
Yes.
Mitogenic means producing or stimulating mitosis.
Okay. So
Oh,
cell division, right?
Mhm.
Okay, so main effects of insulin. Or wait, no, I didn't. Main effects of insulin. Insulin principally acts on three main body tissues: skeletal muscle, white adipose tissue, and hepatocytes, through both direct and indirect effects with both metabolic and mitogenic actions. Insulin's effects via acting on the central and peripheral nervous systems, vascular or endocrine systems, can have systemic consequences. Nutrient metabolism. Insulin orchestrates fuel flux and metabolism through direct and indirect mechanisms with major pathways including gluconeogenesis, glycogen synthesis, and suppression of proteolysis or lipolysis. Hepatic glucose flux, gluconeogenesis, glycogen synthesis is regulated through insulin, fuels, and glucagon working in concert. Insulin suppresses gluconeogenesis directly via gene transcription and indirectly via suppressing lipolysis, or reduction in substrate availability. It also suppresses glucagon release by the reduction of enzymatic expression and or activity. Insulin is well recognized to have anabolic effects in human skeletal muscle, predominantly through suppressing proteolysis.
So the anabolic is building muscle, correct?
Yeah.
Okay. Whereas catabolic
And then
is
catabolics breaking it down.
Yeah.
okay.
Okay.
I'll read the next little section. Electrolyte homeostasis. Insulin lowers serum concentration of phosphate, potassium, and magnesium by promoting cellular uptake. Within the renal system, insulin promotes sodium reabsorption in the distal nephron and may promote calcium excretion.
Okay. And then the next two little headings, dark headings, are also in the same section you're reading.
Okay. Nervous system. I kind of wanted to talk about that for a second, though.
Yeah.
So, you know how when you go keto initially and you don't need as much insulin, so your electrolytes get out of whack because you don't need as much water to process that insulin. So you're shedding all this water, you're shedding all these electrolytes. I'm just wondering, I was trying to relate that to what I just read. Like I said, insulin lowers serum concentration of phosphate, potassium, and magnesium by promoting cellular uptake. So it's basically helping push those into the cells, right?
Well, it makes sense that there would be kind of a delayed reaction to insulin adjusting to the change in the diet.
Yeah.
So I know that I hear people talk all the time about how initially when your body's transitioning, into ketosis, that supplementing the electrolytes are important.
Yeah.
But once you've adjusted, a lot of people don't continue to need them.
Yeah. Yeah. Because you're getting it from your food. I just wondered if it was related to what I read, but I don't think it is. I think that's more of just like what insulin's doing at baseline versus what I was thinking of is more of I don't want to say an unnatural thing, but like a change, like a huge change, like a fluid shift. So that would be totally different. But
well, I mean, since insulin affects the cellular uptake of these electrolytes, you would think that if all of a sudden your insulin isn't needed, we'd have like too much of these electrolytes, not too little.
well, but then you're losing the water. So that's your electrolytes are going with the water. So I don't know. It's just my brain trying to put the picture together. But I did want to mention something that's really been interesting to me. And that is when I was on keto, I used to have, sorry about the motorcycle driving by.
Oh, I didn't even hear it.
That? Okay, good.
I didn't hear it.
Good. When I was on keto, I used to have like cramps, calf cramps all the time. And it really worried me. It made me think, gosh, am I doing something wrong? Because like I've been keto for all this time and here I am still having calf cramps. And I was strict keto. But I will say on carnivore, and I've asked Dr. Chafee this before, he didn't really give me a super great answer on it. No offense, Dr. Chafee, but it wasn't exactly, it didn't make sense to me. Like it didn't resolve it for me. But on carnivore, I never have calf cramps ever.
Interesting.
So I'm just like, do other people experience that and why? I've always wanted to know why.
I don't know. I mean, the first time I did carnivore twice. This is, my second time doing it, but the first time was only 6 weeks and I stopped because of the calf cramping. It was one of the reasons I stopped, but I was getting bothered by the fact that I was having calf cramping, but I wasn't supplementing any electrolytes as I was transitioning my body over then. Yeah. And then when I started it again last year, I did supplement. So I was more of the traditional, person that needed the electrolytes. So I
needed them at first, but I also supplemented them transitioning into keto. But like I'm talking 6 months into keto, I would still have calf cramps from time to time. And I've just noticed that I never, ever have them on carnivore. And it's just really, it's something that's definitely a noticeable difference, But anyway, if anybody knows, let me know.
Yeah, definitely. Oh.
Okay, so
we did get a comment from Charlie. Okay. Charlie says, "I've never had a calf cramp." Oh, good. And he has monster calves, so you guys can figure. So are they going to be more prone to cramping?
It makes me think though that like I'm doing something right with carnivore, and
yeah.
And I'm not even 100% carnivore. Like I'm just, there are times when I will eat something that I want to eat, like some berries or whatever. But my carnivore and my keto, it's totally different, So anyway.
Yeah.
All right. So nervous system. Insulin's pleiotropic effects are well demonstrated in the nervous system, where its effects on glucose and energy homeostasis are more indirect via insulin's essential roles on neuronal health and development. While insulin is essential for both central and peripheral neuronal growth via activation of the AKT pathways due to the predominant expression of GLUT1 and GLUT3, neurons are considered insulin responsive rather than insulin dependent. In the central nervous system, insulin is transcytosed across the blood-brain barrier, where INSRs are widely expressed, especially in the hypothalamus, hippocampus, and cerebral cortex, all of which are involved in regulating metabolic homeostasis. Brain insulin signaling is pivotal for regulating the hypothalamic pituitary adrenal axis, promotes synaptic plasticity, influences proliferation of glial cells, and has a central role for the glycemic control with mechanisms yet to be fully determined, thus highlighting insulin's significant role within the brain. Vascular system. Within the vascular system, insulin has a number of vital roles, especially in vasoconstriction and coagulation. INSRs are widely expressed on both vascular endothelium and platelets. When insulin binds to the endothelial receptors, it activates endothelial nitric oxide synthase. The subsequent production of nitric oxide prevents vasoconstriction, inflammatory cell adhesion, and platelet aggregation to the endothelial wall. With respect to coagulation, insulin modulates platelet aggregation, preventing overactivation, while it also modulates fibrinolysis, thus impacting many aspects of vascular health.
Whew.
It's actually really fascinating, all that insulin does.
Yeah, so we don't want to completely get rid of insulin, and we couldn't even if we wanted to.
Right.
But
As
you
long
know,
as you have a functioning pancreas.
yeah,
Mm.
You just don't want
Yeah.
insulin to go haywire through your body, because too much of a good thing can be a bad thing.
Yeah, I mean, basically, it sounds like our body will produce the basal amount that we need. It'll spike in response to what we eat, but it's perfectly capable of producing that basal level that we need
Yeah.
to support all of these systems.
and that basal level is keeping us from getting blood clots, keeping our platelets from aggregating together inappropriately and
Mhm.
overactivating, and insulin is also stimulating nitric oxide, which we know nitric oxide synthase, which we know nitric oxide makes you vasodilate, and
Mhm.
I think it plays a role in inflammation.
Yeah, I mean, anybody who knows someone who has nitroglycerin tablets for their heart, that would be the same concept. It dilates your vessels.
Oh, I hadn't thought of that.
Yeah, so I did look
So-
up transcytosed because that was a word I didn't know. When it's talking about the nervous system, it says insulin is transcytosed across the blood-brain barrier. And that is basically, it's a process that takes the material from one side of the cell, transports it in the form of a membrane-coated vesicle through the cell for its release on the other side. So I guess it coats the insulin and draws it into the brain and then releases it into the brain. I'm assuming it's probably something fat soluble, because my understanding is it has to be fat soluble to cross the blood-brain barrier.
I believe that's
yeah,
right.
so that's interesting, as opposed to where it was talking before about the normal, like the gradient that would cause it. You get the potassium release, the calcium. They'd switch places and create this gradient of electronegativity, which would open the gate, pull the insulin in. This is the insulin gets coated and gets drawn into the brain. So it's a different mechanism, which is interesting. Yeah. So, okay. So the next section is like a higher level section, 1.2.2.3, called insulin resistance and hyperinsulinemia. And the first section underneath that is 1.2.2.3.1, called insulin resistance important for human survival ? So insulin resistance is a poorly defined concept that aims to explain the pathophysiology of type 2 diabetes. The term itself can be traced to the observation of Hemsworth in the 1930s, where people who required larger doses of insulin to maintain euglycemia were termed insulin resistant. Historically, insulin resistance has a glucocentric focus, which has resulted in increased attention to myocytes, hepatocytes, and remind me what WAT is? White adipose tissue. WAT. And these tissues can manage significant glucose flux and disposal. What has been overlooked is that insulin resistance per se is an important physiological state that is evolutionarily important for human survival. Biochemically, mitochondria use fuels from a variety of sources, for example, glucose, pyruvate, lactate, acetoacetate, and fatty acids to generate ATP, preferably from oxidative phosphorylation, as this generates the maximal amount of ADP and other products, for example, proteins, hormones, and enzymes, with a minimal amount of reactive oxidative species, or ROS, and other undesirable byproducts. Certain cells have a higher glucose demand, including retinal cells, renal medulla cells, red blood cells, and the central nervous system, whereas other cells can use fatty acids and ketone bodies, for example, skeletal muscle. During times of food shortages, especially of carbohydrate-rich foods, example during winter, insulin resistance is physiologically important to ensure that cells with a higher reliance on glucose receive, whereas cells with lower glucose requirements do not use the scarce resource. Furthermore, it is well recognized that different life stages, especially pregnancy and puberty, are associated with transient insulin resistance in healthy individuals. In these instances, insulin resistance is of physiological benefit and necessary for development and growth. This means that insulin resistance can be divided into acute and chronic subtypes, with acute insulin resistance being the physiologically important and reversible subtype for evolutionary survival. Conversely, chronic insulin resistance is associated with the pathogenesis of metabolic diseases, especially type 2 diabetes. Although, as can be discussed in later chapters, chronic insulin resistance can be improved, whether chronic insulin resistance, chronic insulin resistance can be improved, whether chronic insulin resistance can be improved, placed in remission, or reversed, but cure remains uncertain. So we are selectively insulin resistant, even in a healthy state. That's what I'm kind of reading into that. Does that make sense?
Yeah, and like insulin is a growth hormone, so it would make sense, like for example, during pregnancy, that you would have more of it because you are growing yourself and a baby.
Yeah.
So as an example, so
and if your body were not at least a little bit insulin resistant, you and baby might not get everything that you need, because you would be anyway. I don't want to delve too deep into it, but yeah.
Aren't you guys, this is just a side note, aren't you guys glad we're not being tested on this?
Yeah.
Oh my goodness.
Yeah.
We would have to do even smaller sections every week
Yeah.
if we were being tested. I can just
Oh
tell
my
you
gosh.
that.
I mean, we have to keep in mind that this book was probably written for doctors to learn about, the ketogenic state and the benefits of ketogenic diets, on their level. And it's written by doctors for doctors. So,
And it's a reference manual, so to speak, too. I've heard Dr. Westman say that he'll refer to it.
Yeah.
for various reasons.
Doesn't
if
Dr.
question
Barry
comes-
doesn't Dr. Barry have this book, or maybe it's Dr. Ovadia? I was watching one of them recently. Maybe it might have been Dr. Ovadia.
Dr.
Has it
Ovadia
on his
does.
bookshelf.
Oh, well,
On
I
his
guarantee you,
bookshelf
Dr. Barry has
in the
it.
And he
background.
probably does too.
I guarantee you.
Yeah. Oh, we got another comment on leg cramps from Amy. Lots of people have leg cramps, calf cramps on carnivore. They put it down to oxalate being flushed out. Oh, interesting.
But in the
Possibly.
beginning, or like a year or 6 months into carnivore, did they still have them? That was the difference I'm noticing, is that like 6 months into keto, I still had cramps, and I would
If it
expect
was
them at the beginning of
oxalates,
carnivore.
if it was
I don't know that
oxalates,
oxalates
though,
would cause leg cramps.
yeah, I don't know. I mean, the oxalates cause a whole bunch of stuff. So interesting. All
I mean,
right.
I've never been able to pin down anything to oxalates. I don't know about you guys, but
You know, I eat so few vegetables. Like I did eat vegetables before, but I ate mostly garbage, like starchy carb garbage stuff, that I don't think I experienced any oxalate dumping.
I
To be
think
honest.
I may possibly have, like, I mean, it was like back like a long time ago when I started going like really strict keto. I had like this, it wasn't a rash exactly, but it was like red kind of just discoloration like on my neck and on my chest. And it was like it would be a little bit raised, but it wasn't just like this horrible rash. But I'm not sure that's what it was, but I never, and then it just went away. So I don't know what it was. I mean, hadn't used any different soaps or anything. You know, I was just kind of wondering because I didn't want to wear tops, that had any kind of a lower neck because it was just embarrassing to me. But then it went away.
I had this thing come up like probably about 3 months into carnivore, and I don't know if it was due to oxalates. That's my whole thing. Like,
Yeah.
I don't know how you would know, like,
Right.
I don't know how so many people can say, yeah, that's oxalate dumping. I mean, because it's the things that come up for me that I think could be oxalate dumping could also be like a lot of other things. And the thing I had like, it wasn't a sty, but it was some sort of like bump underneath my eyelid. And it was wild. I was sending pictures to Nicole back then, and it was just like my eye just swelled shut overnight. And I've never had any problems like that at all. So that was kind of suspicious for maybe could possibly have been oxalate dumping. Oh, there's Nicole.
Yeah, you talked her up.
Oh, there she is. Your ears must have been tickling or something.
Nicole, do you remember my eye? I was like, what is going on? So we decided that was probably oxalate dumping. But I mean, as far as like being able to pin it down, that's always been my question. Like, how would you know for sure that something was oxalate dumping?
Well, some people, certain types of oxalate dumping, people can know because like it comes through their skin, or they get the crystals, or, I remember interviewing Lisa, who lives in Australia, and she had horrible oxalate dumping, but she was doing like green smoothies like a couple times a day.
Okay,
And
that would probably, that would
she
definitely.
had it, yeah. Oh yeah, she had the crystals come through in her urine. She said it was horrible. It felt like she was passing stones all the time.
Well,
Horribly
now
painful.
I did
And then
have
her
a lot of.
scalp.
I'm sorry to interrupt, but I did have a lot of urinary symptoms. It's just like I'm not doubting it at all. It's just how would you know versus maybe I just passed a smaller what you call it.
Kidney stone?
Yeah, it's like the words, they just don't come in menopause, guys.
But it's a valid question to ask for sure, because that is a question I'm sure people are like, how do you know if this is actually oxalate dumping if you don't actually see the crystals?
I will tell you one thing that I experienced that somebody said might have been oxalate dumping, but I thought it was actually from yeast. Yeah, the donuts outside the hotel. We'll have to explain that here in a second. But the donuts. My yeast symptoms got worse. And I've seen this in the past when I did keto. They got worse at first, but they got like outwardly presenting worse instead of usually they're more like calmed down, but they're inside and mainly in my gut and, even in like my throat and stuff like that. And I was seeing more evidence on the outside, and it was just kind of strange. And I thought, is that yeast? Is it oxalates? Is it like, what is going on here? But anyway, it's just interesting.
Well, whatever it might be, it sounds like for both of you that there might have been just some detoxification going on through the skin.
For sure. Yeah. Okay, so Nicole and I stayed in a hotel at Ketopalooza, and we were like, "Oh, this is a nice hotel." It was owned by the Hilton, right? No, the store across the road had bars on the windows and a security guard in there, and I didn't know that until I went in. She waited out in the truck. I go in, I'm scared to death. Like I'm standing in the line, like, what is going on here? And I finally get through, and then these two big guys follow me out, and Nicole's like, I didn't know if I was going to have to come rescue you or not. So she opens the door, she unlocks the door, and I jump back in real quick, and we go back over to the hotel. And then 3 a.m. in the morning, people are literally doing, how you'll see on TV in these bigger cities where they're doing donuts in the intersection? Yeah.
Well, those type of donuts.
Right in front of our hotel.
Oh.
Yeah.
Oh, my word.
It was scary. And I'm like, Nicole, and then we got back to the hotel. We got back to the hotel and we had to park on like way far away on the side of the hotel. And we get out and all I see is Nicole. Like here I am trying to gather up all my crap and I'm very vulnerable because I got so much crap, And I look and there's Nicole and she's standing at the back of the truck and I see her. She's got her eyes locked on something. And I hear people talking and I'm like, what's going on? I was scared to death. Like I was about to take off running, but I had so much crap I couldn't.
I guess you could have
yeah, I mean, there were some people that were like watching us kind of from a distance, and she's like, because she used to be a cop, and she was like, I was trying to feel it out and see, if something was getting ready to go down or what, and I mean, I haven't felt my heart pound out of my chest that much in a long time.
Wow. Now, is that going to be the same location that Ketopalooza is going to be at this year?
So Ketopalooza wasn't at that location. We stayed a ways away. Like it was, I guess it was like a few blocks away, but it was a totally different environment. Yeah. This year, if I go, I'm staying at the hotel that Ketopalooza is at. So
yeah. Okay.
And it's it's a really nice place.
I'm considering going. So
yeah, it's a really nice hotel.
It looks nice from the, okay. All right. Whew. That would have scared me. Okay. I think I just finished my section. Okay. Let's see what we have coming up here. You want to take, Carrie, you want to take that next section, and there's a few little subsections in it. So just go ahead and read through those.
Okay. And we are at 1.2.2.3. Is that correct? Or are we down to 1.2? Are we down? Which one are we on?
The physiology and pathophysiology of insulin resistance.
Okay.
Yep.
All right. All right. 1.2.2.3.2. I'm sorry. That just cracks me up. Anyway, physiology and pathophysiology of insulin resistance. Traditionally, the biochemical principles behind chronic insulin resistance and acute insulin resistance are similar and revolve around glucose disposal in the skeletal muscle, which is a major site of insulin-mediated glucose disposal. Most glucose taken into skeletal muscle is converted to glycogen to be used as a local energy source and cannot be re-released back into the bloodstream for other tissues. Therefore, inducing insulin resistance in skeletal muscle was vital for surviving in evolutionary terms. In times of poor food availability, adequate glycogen could be locked away in skeletal muscles for the fight-flight emergencies, while fat was used for basal energy expenditure and the body's glucose, primarily from hepatic gluconeogenesis, used for the other tissues that had a higher physiological need for glucose. Acute insulin resistance can help within hours with triggers such as short-term stressors like pain, fasting starvation, acute stress, or impaired sleep, and are believed to impart increased rates of survival. By contrast, insulin resistance chronic is believed to develop over years, if not decades.
Okay, so I have a question about this one. So, am I understanding that once the glucose is in the skeletal muscle, it stays there until it's used?
That is what it sounds like to me, and I've never heard that
It says it
before.
can't,
Okay.
yeah, it says it cannot be re-released back into the bloodstream for other tissues.
So it's
Okay. So two things. One, I don't know. And two, I do know they say that if your blood sugar's high, you can do calf pumps. You know how you do like calf raises, like just basically go like this up and down on your feet. And that will help bring your blood sugar down because your calves are such a huge muscle that use so much sugar. So, but as far as it actually being in there, like it's just stored in there, I guess.
That's what it says.
I don't know.
It says,
Oh,
yeah.
help. Help.
Yeah,
it talks
yeah,
about,
help us out
but
here.
it says it's locked away in skeletal muscles for fight, flight, or flight, fight emergencies.
Yeah.
So
and it
it's
says
locked
Oh,
into
as
those
glycogen,
muscles.
she said.
So in case you have to, so the muscle itself uses it. It's not that it goes anywhere else.
So I always think of like glycogen storage being in the liver. That's what I'm getting.
But this says that in the skeletal muscle, it's converted to glycogen there to be used for a local storage energy source. It cannot be re-released back into the bloodstream for other tissues. So it looks like our
Okay.
muscles do the same thing.
So, and just until the muscles actually use it.
Yeah. Yes. It's sympathetic nervous system stored in muscle and liver. Yeah. Okay. Cool. So we learned something.
Okay.
I thought it was just the liver too.
Yeah, it says that skeletal muscles store about 3/4 of the body's glycogen.
Okay. That's interesting.
Yeah.
So I know that, they say that exercise is really good for blood sugar,
Yeah.
that it'll bring your blood sugar down. So I guess you're using your, now maybe Nicole or Cynthia, if you're still here, can correct me on this, but my understanding would be, just thinking through it logically, that if you're using the glucose in your muscles and using up those stores, it will then allow more glucose to come in, and which will then lower your blood glucose. Does that make sense? It basically empties the storage bin, allowing more to come in and from your bloodstream systemically, lowering your blood sugar.
Yeah, that makes sense.
Yeah. Okay. So she said, correct. When kicked into fight or flight, that's when it's released along with adrenaline, cortisol. So exercise. So does it need to be high intensity or medium intensity exercise in order to get that release?
I mean, I've heard that just walking just the calf raises will lower your blood glucose. So that's what they say.
That's what they say. What if the calf raise is like simulate running without actually having to run?
Yeah, just going for a walk, she said.
Okay. Oh, cool. So Amy says, yes, I believe that the sugar stays in the muscle, and what the muscle can't use, the body stores. The glucose is fat inside your fat cells. That's the way I understand it. Okay. Yeah, just going for a walk. Cool. Cool. Pretty sure that my left thigh is where all the Snickers bars are.
Nicole, you just pop up at the most opportune time for my
I know. Just when we need help.
Just when I need her There she
Maybe
is.
has,
Ta-da-ta-da!
You have a cape now,
maybe has the
Nicole.
Snickers bars in her left thigh and the Oreos in her right thigh.
That's great.
You've got smart muscles. They know exactly which sweets they like the most. Okay. So anyways, sorry, I know I interrupted, but I really wanted to
No,
make sure I
it's
was
good.
clear on that.
All right, acute insulin resistance. This means that the mechanism for insulin resistance acute is prominently the inhibition of GLUT4, especially in skeletal muscle. Although insulin or muscle contractions induce the translocation of GLUT4 to the cell's surface, a variety of processes can impede GLUT4 translocation, including acute pain or injury, corticosteroids, sympathetic activity, and pregnancy. The precise mechanism by which fasting induces insulin resistance in humans has not yet been resolved. However, elevated concentration of glycogen and increased lipid accumulation have both been observed after a 72-hour fast, and both mechanisms decrease GLUT4 translocation. In hepatocytes, insulin resistance acute results in increased gluconeogenesis. Key features of insulin resistance acute are timeline and reversibility. Insulin resistance acute is generally associated with a clear timeline and or endpoint, like pregnancy or winter, or a short-term challenge like an injury, where the person would either survive or die. It can also be swiftly reversed with removal of the challenge, for example, childbirth or increased food availability. That makes sense.
Okay.
Yeah, I mean, that makes sense. Does anybody have any questions about that? I actually believe I understood that.
Yeah. Basically, acute insulin resistance. So we're talking insulin resistance. So I'm assuming that goes back to where it said that there's our body will like make certain parts insulin resistant in order to provide the glucose for the parts that need it. So I'm assuming that ties into that.
Mm-hmm. And so acute also just means that it's not a permanent thing. So you're temporarily insulin resistant, and then it goes away when the need isn't there anymore.
Mm-hmm.
Yeah,
Okay.
but tell my body that, because I had 4 babies and I feel like my insulin resistance did not go away for a long time. And you know how they say, oh, if you breastfeed, you'll just drop weight like crazy. That's a lie.
That's a lie. So,
All right.
okay. So, all right. I want to make sure I'm clear too with these, the glutes. These are the glucose transporters. I know that there's several of these types of glucose transporters. I need to refresh my memory that this is their the GLUT1 and 3 are predominant in the pancreatic cells. So it's saying that it will actually, with acute glucose, it actually inhibits these transporters. So I guess that means that it's inhibiting the ability for that particular tissue to bring in more glucose.
Okay, I found something here. It says GLUT1 is the major glucose transporter in brain, placenta, and erythrocytes, or red blood cells. GLUT2 is found in the pancreas, liver, and kidneys. GLUT3 is neuronal and placental, while GLUT4 is the insulin responsive transporter found in skeletal, muscle, heart, and adipose tissue.
Okay, so that makes sense because it talked about the inhibition of GLUT4 in when there's acute insulin resistance. So it keeps the GLUT4 from getting to the cell surface.
Mm-hmm.
Okay.
So they're what
this is hard
moves the
stuff.
glucose. The glutes are transporters that are membrane-associated proteins that help move glucose and other hexoses, which that's sugar, across the plasma membrane. Glutes are classified into 3 classes based on their substrate affinity and sequence similarity. So 1, 2, 3, 4.
Yeah. Okay.
So basically,
Yes.
just differentiating them. The only reason for differentiating them is to, you know, tell which organ they have an affinity for. Does that sound right?
Or they're in the cells of those particular types of tissues.
Yeah, it used the word
It,
affinity, so that's why I
affinity.
used that
Yes.
word.
Yeah.
Because it attaches, right? If I'm remembering correctly from biochemistry, it's like floating around and attaches to whatever and then helps the insulin go through. Is that
Mhm.
accurate? I need to go to
Yeah.
medical school just so that I can understand the human body enough to regulate my own diet. So
Yeah,
and
seriously.
then I still
'Cause-
won't understand because they don't teach you about nutrition. So then I'll have to go to a nutrition school on top of that.
Well, yeah, but good luck with that because you know what they teach.
I know. I mean, maybe just a degree in biochemistry and I can figure it out myself.
There you go.
You know?
There you go. But it does say that usually insulin or muscle contractions will induce the basically movement or translocation of the GLUT4 to the cell surface. But yet when you're dealing with acute insulin resistance, these processes like acute pain, injury, that sympathetic nervous system fight or flight thing actually prevents that GLUT4 from getting to the surface of the cell to allow, I guess it keeps the cell from bringing in insulin to help lower your blood sugar, your glucose in the cell, because your cell needs it at that point because you got an acute situation. So it keeps you it becomes insulin resistant that way. It doesn't even go there to get to let the insulin in when you have an acute situation.
Thanks, Sandra.
I agree, Sandra.
Yes, I agree.
And so would Lynn. So Lynn, I need you to join me in medical school, please.
Oh my
or at least
goodness.
in biochemistry school.
Biochemistry.
We need to be biochemists.
You know what? Years ago when I was still in college and I was working on a degree and stuff, I was working in a lab and I thought I wanted to be a microbiologist for a while. But I was working in the public health lab as a lab assistant for about 1.5 years when I was in college.
My mom is a medical micro. Well, she's a medical, not a She's a lab technologist, is what she is.
Yeah.
So she does like microbiology stuff.
Yeah.
She's retired now, but
Yeah. Okay, cool. Okay, so I think I understand the acute insulin resistance mechanism.
Yeah.
Well, the good news is the chronic is by contrast, so that must mean that it's opposite.
Okay.
In my simple brain. Okay, so we have chronic insulin resistance. By contrast, insulin resistance chronic is due to a combination of decreased insulin receptor, INSR, expression at a cell surface, receptor deficits, and impaired signal transduction, post-receptor deficits. Okay, that was a mouthful. Due to a combination of decreased insulin receptor expression at cell surface, meaning receptor deficits. So in other words, the receptor isn't working right. The receptor is not working right to get it in there.
Yeah.
And impaired signal transduction. Or it could be a defect after receptor, right? Post receptor being after the receptor did its part, then something wasn't working right. Is that right?
So I'm reading that is there's either a defect at the actual cell surface, or there's a defect in the ability to bring the GLUT4 to the cell surface.
Okay, and this is where they're talking about, like when you hear the typical explanation of trying to shove it into the cells, maybe it's like trying to shove the fat or the glucose or whatever.
So those receptors are the ways that it attaches, and it's kind of like a channel that. So the way I was reading as um, a decrease of insulin receptor expression at the cell surface. So in other words, the channel's not attaching to bring the insulin into the cell,
Okay.
and impaired signal transduction or post receptor deficits. And I think that's just like a problem with the receptor working properly. I don't know. What do you think?
Well, one may be more of a physiological defect, and whereas one might be a signaling defect. Like the actual morphology of the cell receptor may be defective versus the ability to communicate could be also defective.
Post receptor defects. So post
So that would
receptor,
be
wouldn't
what-
that be like the receptors attached there, but it's just not working?
Yeah,
to get
something ain't
insulin into the
working.
cell?
It's not working. Yeah.
I don't know.
Yeah. That's okay. Okay. However, it is likely that a combination of chronic insulin resistance and hyperinsulinemia is required to develop the pathologies associated with chronic insulin resistance. A decrease in INSR numbers means that a higher insulin concentration, compensatory hyperinsulinemia, is needed to achieve the same biological result, while impaired signal transduction means a decreased biological response, no matter the insulin concentration. Okay. I think I get that.
Okay, so basically that's what the doctors usually say when they say, they'll describe insulin resistance one of two ways. And I think this is actually a combination of those two things. And one is some doctors you hear will describe insulin resistance as it's just not working properly. It just quit working good enough, like the insulin quit working good. And then the other is the other way that you hear doctors describe it, and which is basically that you have way too much but it's not getting through. Is that
Yeah, that makes sense.
Liam?
That makes sense.
What are you doing?
I had to mute myself and tell my husband to shush. He's over there talking to himself.
Well, tell him to come on in.
Oh, you don't want him talking about this stuff. He doesn't know any of this at all.
Oh, stop it.
Well, I don't either.
He probably does after watching us for long enough, right?
Hopefully. But I'm like, shh, quit talking to yourself. He talks to himself all the time.
But sometimes it's just a matter of like breaking the words down, like one at a time. Like, I
Right.
feel so bad for these doctors that have to study this stuff, because as Running Tap says, I'm trying to remember what's her Jeannie.
With two N's.
Yes, as Jeannie says, the body is so complex. It is so complex. And sometimes I would think to study, they probably have to like break down every single word. Like, what's this word mean? Okay, now let's put it all together,
And if they're in a class, they should have an instructor. So I'm
yeah.
assuming that helps.
Yeah, but you know how much reading these college classes make you do on your own every single night? I mean, just getting my degree initially, well, when I was attempting to get a degree at big university before I went to nursing school, I mean, there were like hundreds of pages every single night to read. And it wasn't necessarily in medicine. It was like anthropology. And I can't sit and read without falling asleep.
I can't either. Textbooks to me are a perfect cure for insomnia. So
yeah, because I will fall asleep immediately. That's why this is good, because I could never just sit by myself and do this. So
No, I couldn't either. And I'm learning so much.
Yeah, me too.
It's just great. And the camaraderie and everything. This is fabulous. I enjoy this.
I know, me too.
Okay. So within skeletal muscle, chronic insulin resistance is a combination of INSR and post-receptor deficits, resulting in a blunting of insulin's ability to both translocate GLUT4 to the cell surface and stimulate glycogen synthesis. This leads to impaired results in compensatory hyperinsulinemia.
You skipped the line. You
Oops, I
skipped the
sure
line.
did. This leads to impaired uptake of glucose from the bloodstream. There we go, which leads to glycemic stress on other tissues, including the pancreas, which results in compensatory hyperinsulinemia. You can't see it, but I'm running my finger on the lines so I can keep track of what I am. There you go. Interestingly, insulin's mitogenic effects on skeletal muscle are not impaired and may even be enhanced due to compensatory hyperinsulinemia. In hepatocytes, through a variety of complex biochemical mechanisms, both increased insulin resistance, resulting in increased hepatic gluconeogenesis, and increased insulin action, increased lipogenic flux, are observed. This paradox is believed to result from a combination of hepatic insulin resistance and insulin-independent pathways. Insulin resistance results in inadequate suppression of gluconeogenesis and a decrease in hepatic glycogen synthesis, while insulin-dependent nutrient-sensitive pathways drive the reesterification of circulating fatty acids and de novo lipogenesis to increase hepatic triglyceride concentration.
That was a mouthful.
Blah, blah, blah. It was.
I'm going to have to probably read
Yes.
that.
Yeah, me
Yeah.
too. The one thing that stuck out to me was, interestingly, insulin's mitogenic effects on skeletal muscle are not impaired and may even be enhanced due to compensatory hyperinsulinemia. In other words, your skeletal muscle is building itself up, right?
Mhm.
Even in the hyperinsulinemic state, or is capable of doing so.
Yes,
That was
that's
kinda
what I
what I
read from that too. Yeah. Oh, so this helps explain the whole thing, the thing we were talking about before, like a mechanical engine. If a sensor goes on the blink, the whole engine fails. So
Yeah.
it could be like that.
Yeah.
So
Or even a fuse. If you have a fuse go bad.
yeah,
So
I'm gonna have to
imagine
read this. I'm gonna have to read
the
this.
GLUT4 transporter, or the GLUT transporter, is the I'm thinking of a, not a sensor, but a
Like a spark plug.
Ah,
Yeah, you got a spark
I'm just
plug
making
that's a
stuff
duck.
up now.
so we have mitochondria as the powerhouse of the cells, and now we have the glutes as the spark
Ugh.
plugs.
They're the spark plug.
Why not?
Yeah.
I mean, it relays, the spark
Yeah.
plug relays the spark
It sure does.
through the, I mean, I don't know.
Makes sense to me. Okay.
Okay.
So WAT is both a, okay, what did that stand for again, WAT?
That was the white adipose
White-
tissue.
Yeah.
White adipose tissue is both a nutrient sink and an endocrine organ. Okay, what does
Yeah.
that mean?
I remember learning that the fat was actually like an organ, and that blew me away.
But then what is a nutrient sink?
Let's see
I
here.
mean, that term doesn't
how'd they
make
spell
sense.
it? Is it SYNC or SINC?
No,
No,
it's
it's
SINK.
SINC. Yeah, like the sink in your kitchen.
Maybe they put the wrong sink in there. Maybe this is an editorial error.
I don't know. I'm gonna look that up because I'm
What
curious.
is a nutrient sink? Let's see here. Oh, this is like about waters in the
It's
environment.
just a place that stores nutrients for later use.
Okay.
So storage.
The fat does that? Well, I guess it does, because it stores, I mean, it stores energy. It can store your fat or your sugar as fat for later use, right?
Mm-hmm.
Yeah, so okay, that makes it. It's just us.
I mean, those are nutrients.
Yeah, that just
I don't
when
know.
I first read that, it just didn't make sense. Okay. Although not a significant site of insulin-mediated glucose disposal, less than 5%, This process is necessary to generate glycerol 3 phosphate needed for fatty acid esterification and correct lipid storage. Therefore, insulin resistance in white adipose tissue results in incomplete suppression of lipolysis and improper lipid storage, thus facilitating lipid storage in non-adipose tissues. The etiology of insulin resistance in white adipose tissue remains the subject of debate. However, what is recognized is that hypertrophy of white adipose tissue induces low levels of chronic and systemic inflammation with an increased release of cytokines, especially from visceral fat deposits. Despite insulin per se being anti-inflammatory, the net effect of hyperinsulinemia is increased systemic inflammation due to increased visceral obesity, and so it will be described accordingly. Wow.
So this reminds me of what I was hearing during the pandemic. They were talking about how obesity was a higher risk for having serious illness, and they were talking about this very thing about the fat tissue releasing cytokines.
Mm-hmm.
Oh yeah.
I've
yeah.
heard that. Yeah.
Yeah. So that sounds like that's what this is that when you have hypertrophy or larger, bigger or more fat white adipose tissue, there's low levels of chronic and systemic inflammation with an increased release of cytokines. So I would imagine if you're already having cytokine release from your fatty tissue when you're not sick, it's probably set you up for being worse when you are sick. And I don't think this is something that's I can't imagine that this is something that's just like a viral illness. It would seem like any illness could cause issues like that.
Mm-hmm.
Putting your body under stress. So interesting. All right. Well, I'm probably going to have to read the last two paragraphs again.
Yeah, that's why I will go back and listen to us again, like just as I'm cleaning the house or something, because when I'm reading, I'm just thinking, am I saying that word right? Am I going fast enough? Am I going too slow? Do I sound stupid? Have I mispronounced too many words? So like when I listen to it again, then I actually absorb more of it.
Yeah. So awesome. Well, why don't we stop there?
Okay.
This
Sounds
week.
good.
And we will pick up on the next section next Thursday. Same bat time, same bat channel.
Let me show y'all what's coming up.
Oh yeah. And oh yeah, that is. Oh yeah, that's on the next page. All right, the gingerbread man.
Yep.
In a keto book, which seems very ironic.
Yes, it is.
Yes, that is ironic.
Well, thank you guys for showing up and contributing to the discussion and providing such good info. Especially Amy and Nicole. You guys really gave us some info.
And Cynthia.
Yeah. Cynthia's here early on. That's right.
Yeah. Well, I mean, I'm thinking everybody, but just like
and
the
everybody.
actual, like mechanism of action of
But the technical stuff for sure is very helpful, because I don't mind admitting if I don't quite get something. I much rather ask and gain an understanding than to pretend like I know it.
And I mean,
absolutely.
None of us learned this no matter what school we went to, none of the three of us learned this stuff. So like we might have gotten a little bit brief exposure to some of it, but not on this level and not in this way that this is being presented, So we're all learning as we go. And I mean, I don't ever hesitate to say, I don't know, because I figure after being a nurse for 24 years, if I don't know, there's probably somebody else out there that doesn't know also. So,
And to be honest, how many of the doctors out there actually even take this course?
Yeah.
Right.
They would have
I would say it's probably difficult.
Yeah, they would have to purposely take a course. Maybe doctors that deal with childhood epilepsy might want to study this because the ketogenic diets are used for that. But I think, there's probably most doctors probably don't even go through this course at all.
Well, hopefully in the future, the ketogenic diet will be used for much more frequently. So, hi, Dr.
Absolutely.
Neil.
Oh,
Hey,
hey,
Dr.
doctor.
Nelson.
hey there. Just as we're
Dr.
wrapping up,
Nelson.
someone who absolutely has studied this book.
Yes.
Yeah. So, yeah, Dr. Nelson, we are just wrapping up. You caught us right at the end. So nice to see you here. And
Yeah,
thank you
we're
for
glad you
sending
popped
that
on.
in for that booklet. That was very
Yes,
thoughtful.
Oh,
thank
yeah.
you.
Yeah. Thank you for that.
So, yep.
All
All
right,
righty.
guys.
Well, we're signing off for today.
Well, let's
We
tell
will.
everybody they can come see us at Lynn's at Midlife Carnivore. I am at Carnivore Nurse Kim, and Carrie is at My Meatomorphosis with an O.
With an O.
That's
So
right.
we'll see you next week.
And no worries, Dr. Nelson. Glad you came.
Yep.
All righty.
Hopefully
See
we'll
everybody
see you
next
next
week.
time.
Yeah. All right.